All right, Algebra 1. This is our second lesson. In this video, we'll cover the second lesson in the Academy's Algebra 1 course, which covers articles 16 through 38. So if you want to look at the textbook and take a look quickly at articles 16 through 38, that's going to be the content of this second lesson. Simple stuff. If you've studied arithmetic, this is simple stuff. This is not complicated. But we're just going to go through, make sure everything's clear, because like I said, when students struggle in algebra and in advanced maths, the causes of their struggles are almost always simple definitions. All right, simple concepts, things like that. Let me let a couple more people in here. Okay, so Algebra 1, in our first lesson, just to go back over our introduction real quick, we talked about high school mathematics. We said in high school mathematics, selective colleges want to see 4 years of high school math studies. Most high schools only require students to study for 3 years, to complete 3 years of math. But selective colleges want to see 4 years of math studies. A year of math studies is equal to 120 hours. 120 hours of math times 4 years of study produces a total of 480 hours of high school mathematics for a high school diploma. It's a lot of math, all right? It's a lot of time devoted to modern mathematics. It's time that takes away from other studies which are more important in your life. And that's why it's important for us to study modern mathematics in an efficient way. We have to find a way to study and master modern mathematics in a way that's efficient. It has to be clear and simple and effective. We can't waste time in mathematics. Most students, I would say, spend 4 years studying math in high school and barely learn the content of those math subjects. We want to do better than that. A high school math program consists first of algebra, which we'll call Algebra 1, then modern geometry. In the Classical Liberal Arts, we study that in the Classical Liberal Arts Academy, we study modern geometry and plane and solid geometry. That's the name of the course. In the third year of high school, Algebra 2. A second year of high school algebra. And then, as I've explained in other introductory lessons so far, that's where the SAT test stops. So the SAT, the test that's used for college admission, the math section on the SAT only covers Algebra 1, Algebra 2, and modern geometry. And as I said in another video, another lesson, if you try to rush through these to get to higher maths, you may hurt your SAT score, which doesn't make any sense. You should only worry about higher maths if you have a good SAT math score. If you don't have a good SAT math score, you should take your time and continue studying these maths until you get a good SAT math score before you worry about any higher maths. Your SAT score is far more influential. To continue studying into a fourth year of high school math, the next subject would be trigonometry, which is another branch of geometry. If you look in the textbook that we use for modern geometry, plane and solid geometry, if you look in the table of contents, you'll see that the last section of that book is trigonometry. The fourth high school math is trigonometry. And then the fifth is calculus. And even into college, that's usually where math studies end. Math studies end in calculus. Few students will ever need to go that far in math studies. And as I said, trying to race through this so you can boast of completing all of these courses in high school and not learning any of them well will give you a low SAT math score. It's just not worth it. It would be better to limit your studies in high school and get a good math score on the SAT. Or, in the ideal situation, which we'd like to seek, study each of these carefully for mastery and get both a good SAT score and complete the highest levels of math studies. That's perfectly possible, especially, like I said, if we have a source for studying high school mathematics that's efficient, that actually allows us to master the mathematical sciences without wasting time. And the textbook series that we use in the Classical Liberal Arts Academy for Modern Mathematics, which is Ray's Mathematics, it's the most efficient source of modern math studies that you can find. You can find better books. You can find better textbooks. You can find online programs that teach mathematics, but none of them will teach the entire body of high school mathematics as efficiently as these old textbooks do. And that's why I recommend them, because we want to master modern mathematics, complete our high school studies, satisfy all these requirements, and we want time to devote to more important studies. So we have more to think about than just getting good grades in math. We have philosophy, theology, history, literature, all these other studies that are just as, if not more important, that we have to get to. But Algebra 1 is the first of the high school maths. In our first lesson, we talked about what algebra is. We talked about what algebra is, and I don't want to get back into all that stuff in this second video. So if anyone is watching who didn't get a chance to see that, go back and watch that first video where we talk about what algebra is. We have a definition of algebra in Article 15. In Article 15, our textbook says, algebra is a general method of solving problems and demonstrating theorems by means of figures, letters, and signs. What you need to focus on there is algebra is a general method. It's not working to solve specific problems where the numbers are known. Algebra is a general method of solving problems. And we talked about why a general method is needed. In our first lesson, we talked about how there are many things that we need to solve, many problems we need to solve, where the numbers are constantly changing. And when the numbers are changing, what we need are formulas that explain the relationships between the different quantities. And that's what we study in algebra, the general method of solving problems and demonstrating theorems where we don't necessarily know the numbers that need to be used in the calculations. And that's why we represent quantities with figures, letters, and signs, because the actual quantities may change. Algebra is a general method of solving problems and demonstrating theorems. So I recommend you re-watch the first lesson video if you'd like to cover anything in Articles 1 through 15. And in this lesson, we're going to move on through Articles 16 through 38. Articles 16 through 38 contains a lot of information. There's a lot of information in Articles 16 through 38, but it's simple information. It's just the study of the signs and symbols that are used in algebra and some more definitions. So nothing really complicated or confusing, but there's just a lot of stuff, and we cram all of this into the second lesson so we can keep moving forward. So let's just walk through this second lesson, Articles 16 through 38. Article 16, we talk about two different kinds of quantities. Two different kinds of quantities, and we've already talked about this. Known quantities and unknown quantities. There are quantities whose value we know in mathematics, and there are quantities whose values are not known. They're unknown quantities. Known quantities are those whose values are given. So when we have some problem to solve, some mathematical question to seek an answer for, there are going to be quantities that we already know. Those are called known quantities. And there are going to be unknown quantities which we seek. Those are called simply unknown quantities. Article 17 is a little rule about how known quantities and unknown quantities are represented with letters, but I don't believe that anyone actually practices this today. But nevertheless, for the sake of studying the textbook carefully, known quantities are generally represented by the first letters of the alphabet. Unknown quantities are represented by the last letters of the alphabet. Now, why Article 17 is important for us, like I said, it may not be practiced by people in math classes or mathematicians today, but that rule, number 17 there, is going to be practiced in this textbook. And therefore, as we study this textbook, Article 17 is important for us to remember. Known quantities are generally represented by the first letters of the alphabet, and unknown quantities, quantities that we're usually seeking in the problems we study, they're going to be represented by letters from the end of the alphabet. In Article 18, we get started with the signs used in algebra, and these are the same as the signs used in arithmetic. That's why I say this lesson isn't necessarily difficult for anyone. It's pretty simple, but there's a lot of information. The principal signs used in algebra are, and then it has a list in the textbook of the signs that we use, the figures or symbols that we use. If you look under the signs, this is what's important. Each sign, each of these signs represents certain words. Each of these signs represents certain words. It's a shorthand. It's a way of writing out mathematical expressions without using words. It saves us time in writing, and when we're writing mathematical problems, it helps us to keep our problems neat and orderly, much more orderly than they would be if we had words all over our pages. So the reason why these signs are helpful is because when we're writing out expressions or solving problems, it helps us to keep our calculations clear and easy to read, which is very important. That's why we use signs instead of the words that they're used to express. They express the words of various operations in the clearest and briefest manner. The other benefit of using signs there is that if there were 10 people in the room, they might all express the operations with different words. When we use symbols, it allows us to avoid that confusion and make everything the same for everyone. And the other benefit is that mathematics can be studied by people of different languages because the signs are common to everyone. It doesn't matter if we have students who speak Spanish and others in French and others in English. If we use mathematical signs, we can communicate mathematically using signs and symbols, and it avoids trouble caused by language. So it allows us to all use the same expressions, even if we differ in language, and that's why mathematics should be considered in some way as a language of its own. These signs represent words, and they express these ideas in the clearest and briefest manner possible. In the following articles, we're simply going to study through the details of each one of these signs. So in Article 18, you have an introduction to the signs, an overview of the purpose of the signs, and then in the following articles, we go one by one through each of these signs. We talk about the expressions that the signs represent, and you should make sure you study these carefully. So again, in this textbook, we want to make sure that we understand exactly what this textbook author means when he uses different signs, so we can read all of his expressions properly. In Article 19, the first sign that we study is the sign of equality, the equal sign. The sign of equality is read, or it represents the phrase equal to. So whenever you see the equal sign, when you're reading the sign, you should read it with the words equal to. The sign of equality is read equal to. It denotes that the quantities between which it is placed, the quantities on each side of the equal sign, are equal. Thus, the letter A, followed by the equal sign and then by the number 3, denotes that the quantity represented by A is equal to 3. And we would read that as A is equal to 3, or A equals 3. Pretty simple. But let's make sure we have all of these clear, since we're going to use these signs and symbols to communicate in algebra. Sign of equality is read equal to, and it denotes that the quantities on either side of it are equal in value. Now, just as a side note, why that's important? Why that's important is because if you have two quantities that are equal, they can be used interchangeably. If you have two quantities that are equal in value, they can be used interchangeably. That's going to be important as you're solving problems in algebra. So if A equals 3, anywhere you see A, you can replace it with 3. Or anywhere you see 3, you could replace it with A. To make it even more useful to understand, if A was equal to B plus C, if A was equal to B plus C, anywhere you see A, you could replace it with B plus C. Anywhere you see B plus C, you could replace it with A. So when we see that two quantities are equal, it means we can use them interchangeably. That's actually what's more important about them. Article number 20, the sign of addition. The sign of addition, which is common knowledge to everyone, is read plus. And the word plus is Latin for more. So the word plus just means more. So 2 plus 3 means that the sum is equal to 2 more 3. 3 more than 2. The sign of addition denotes that the quantity to which it is prefixed or put before is to be added to the quantity that comes before it. Thus, A plus B denotes that B is to be added to A. and we're then given an example. If A is equal to 2 and B is equal to 3, then A plus B is equal to 2 plus 3, which is equal to 5. Very simple. Moving on to Article 21, the sign of subtraction. The sign of subtraction is read minus, or in Latin it's minus, and that word simply means less in Latin. Minus. The sign of subtraction denotes that the quantity to which it is prefixed or placed before, the quantity it is placed before is to be subtracted or taken away from the quantity which goes before that minus sign. Thus, A minus B, the expression A minus B tells us that the quantity B, whatever it is to be taken away from the quantity A, whatever that is. A minus B means that B is to be taken away from A. If A equals 5 and B equals 3, then A minus 3 is equal to 5 minus 3, which equals 2. The sign of subtraction. Article 22. The signs of plus and minus, the plus and minus signs, are also just called the signs. It's kind of a weird rule, but these are called the signs. The plus sign is said to be positive. The plus sign is said to be positive. The minus sign is said to be negative. They are contrary or opposite signs. Article 23, to continue that, we read, every quantity is supposed to be preceded by one of these signs. Every number, every quantity is either positive or negative. Every quantity is either positive or negative. Sometimes we'll see the quantity with this positive sign written in front of it. Sometimes we'll see a quantity with a negative sign written in front of it. If we see a quantity, and this you have to remember, if you see a quantity, a letter or a number, that doesn't have a sign in front of it, it's positive. If I just tell you the number 7, it's positive 7. So when we express positive quantities, we don't necessarily include the sign. We don't say whether it's positive or negative. We always say when a quantity is negative. Sometimes we say when a quantity is positive, but anytime there's no sign added to a quantity, it's positive. The positive and negative signs. Article 24. When two different quantities have the same sign, so they're both positive or they're both negative. When two quantities have the same sign, we say they have like signs. This is going to be important when we study rules, so make sure you pay attention to this. It seems obvious, but when we study the rules, the different rules are going to be for quantities that have like signs, quantities that have unlike signs. Make sure you understand what that means. If two quantities have like signs, it means they're both positive or they're both negative. If they have unlike signs, it means that one is positive and one is negative. Like signs and unlike signs. Positive A and positive B have like signs. Negative A and negative B have like signs. Positive C and negative D have unlike signs. Pretty simple, right? Not too complicated. But remember what I always tell you. It's these simple, basic definitions and rules that cause students to have trouble later on in their math studies. We're going to simply build piece by piece as we study algebra. We're going to go step by step. And if you don't learn one step, it's going to come back and hurt you at a future step. Article number 25, moving through the signs. The sign of multiplication looks like an X. This textbook says the sign of multiplication is read into. I think that's going to be confusing because in modern math classes, we often use into to talk about division. Like, I'm just going to stop there. So into, you may see that in this textbook, and you have to remember that it means multiplication, but normally in modern math classes, if you have other math classes, like in college or whatever, into is not going to be used for multiplication. It's better to read the sign of multiplication with multiplied by. The sign of multiplication is read multiplied by. It denotes that the two quantities between which it is placed are to be multiplied together. And there are a number of different ways to express multiplication. There are a number of different signs that are used, and this is very important. There are 3 different ways. The simplest way is by the use of this multiplication sign. A multiplied by B. But there's another way you'll see. In this textbook it says that it could use a point like that. This is read as A multiplied by B. You'll also see it written in books with the dot a little higher like this, A multiplied by B. And if you see 2 letters together like this, 2 letters written side by side with no sign between them, it's A multiplied by B. Okay? So if you see, for example, if you see 3x, 3x is 3 multiplied by x. 12a is 12 multiplied by a. So there's a number of different ways to express multiplication. We can use this common multiplication sign that looks like an X. We can use a dot on the line, more like a point. We can use a dot raised above the line. Or we can simply place quantities together. Obviously, we can't do this with 2 numbers, right? Because if we took 3 times 4 and put the numbers together, boy, that would be a mess, wouldn't it? So we can't do this with numbers. But we can do this with letters in algebra. So 3 different or 4 different ways that multiplication can be symbolized in algebra. Okay? That's going to be very important, as you'll see in the exercises we do in a little bit. So there are a number of different ways to express multiplication in algebra. You need to make sure you remember them. A, B, written next to each other, express the same thing as A multiplied by B with the X sign, or A multiplied by B with a point, and so on. That's Article 25, the sign of multiplication. To go on with more about multiplication, Article 26, factors. This is a vocabulary term. You're going to see this word used throughout the algebra book. Factors are simply quantities that are to be multiplied together. So the word factors, all that it means is two quantities or more quantities that are multiplied together. So in A times B, A and B are factors. In 6 times 4, 6 and 4 are factors. Factors are simply numbers that need to be multiplied. Factors. Then there's a note in Article 26 about the continued product. And this word product means the result of multiplication. The factors are the numbers to be multiplied. The result of the multiplication is the product. So factors are multiplied together to form a product or to make a product. The result of a multiplication problem is called the product. A continued product in Article 26, the continued product of several factors means the product of the first and the second factors multiplied by the third factor, and this product multiplied by the fourth factor, and so on. So if a number of factors are written in succession, if we see A, B, C, this is equal to A times B times C multiplied by B times C. What this means is the product of A times B multiplied by C. All right, so we simply work two factors at a time to find the product. And I'll write PROD right here as the product. We multiply A times B, find the product, and then take that product and multiply it by C. And we would continue doing that. If it was, there could be 20. This would be equal to the product of A times B times the C, and then the product of that times D, and the product of that times E, and so on, times F. We refer to that as a continued product because we find the product, multiply it by the next factor, find the product, multiply it by the next factor, find the product, and we continue on to the end of the multiplication. Article 27, we move on to the sign of division. The sign of division is read divided by. And just like multiplication, there are a number of different ways to express division with signs. And we'll talk about a few. And I would argue that understanding division and how it's represented in a number of different ways is actually one of the most important principles in mathematics, because many different ideas, fractions are related to division, percentages are related to division, decimals are related to division. So understanding division is a key to many different topics in mathematics. The sign of division, which is a horizontal line with two dots, and think about it, if you look at that sign of division, it's really like a fraction, right? It's like a symbol of a fraction. And a fraction is simply an expression of a division. Even a percentage, if you think of the sign of percentage, it's written as an expression of division. 7% is simply 7 over 100. So this is why I say that this concept of division and the signs of division, the way that division is expressed, is actually very important in mathematics. Okay? The division sign itself is written in the form of a fraction. It's important to keep that in mind. Let's go back to our text. The sign of division is read divided by. It denotes that the quantity preceding it, the quantity before the division sign, is to be divided by the quantity that follows the division sign. The order is very important. You can't write it in any order. The number to be divided comes first, then the division sign, which is read divided by, and then the divisor. So there are the three quantities in a division problem. The three quantities in a division problem. If we have A divided by B equals C, we're just going to use these letters to represent quantities. A is called the dividend. Make sure you know these terms. B is called the divisor, the number that divides, the divider. Dividend means the number to be divided. In Latin, this is a participle, a future passive participle, dividend, to be divided. Divisor, the number that divides, and then the result of the division is called the quotient. In Latin, quote means how many. How many times is A divided by B? The answer is the quotient. Okay, so this number in a division expression is the dividend, the number to be divided, divided by the divisor. That's the number that divides. And the answer to this division problem is called the quotient because it tells us how many times the dividend contains or is divided by the divisor. Okay? Those are the names of the parts of a division. Division is oftener or more often represented by placing the dividend as the numerator and the divisor as the denominator of a fraction. So see here the relationship between division and fractions. If you understand division, you'll easily understand fractions. If you understand fractions, you'll understand division. Okay, so the dividend is the number at the numerator on the top of a fraction. The number written at the bottom of the fraction is the same as a divisor. And you're given an example there. And there are other ways to express this when we're writing, and this differs a little bit from the book. If we look at the dividend and the divider, A divided by B, when we write division, we put the dividend inside of this little bracket. The divisor is written on the side, and then the quotient is written above. A fraction, A over B, is the same as A divided by B. And since A divided by B here equals C, it's the same thing as saying A divided by B is equal to C. So division and fractions are related, and this is another way to express division. This is used when you're actually trying to solve a division problem. This would be used if you're writing an expression with division or the form of a fraction. This is usually used when you're trying to solve and find the quotient in a division problem. Okay? So that's all for division. Article 28, the sign of inequality, which is would be the opposite of the sign of equality, the opposite of the equal sign. The sign of inequality, it's an angle bracket, I guess we could call it. The sign of inequality, we read, denotes that one of the two quantities between which it is placed is greater than the other. The opening of the inequality sign always points toward the greater quantity. This is simple stuff, but let's just make sure it's clear. If we read A, see the symbol of inequality, and B, how do we translate this into a sentence? This is equal to the expression, the quantity A is greater than the quantity B. And if we see A with the inequality sign written in this direction, it means A is less than quantity B. All right, simple, but make sure you understand how to read the sign of inequality. The sign opens toward the greater quantity. A is greater than B. A is less than B, or B is greater than A here. Okay, the sign of inequality. Article 29, the sign of infinity. It looks like a sideways number 8. The sign of infinity denotes a quantity greater than any that can be assigned, or indefinitely great. That's what infinity means. The sign of infinity is a sideways, it looks like a sideways number 8. So if you see that symbol, remember it represents infinity. Now, starting with Article 30, things get a little more challenging. We have to be careful. We have to be careful from Articles 30 down, because we get into some new vocabulary that's going to be very common in algebra, and it causes students to often get confused. So let's be careful as we move to Article 30 and beyond. We're going to see this new word, coefficient. The idea is actually very simple, but it's a word you haven't seen before in any of your arithmetic courses. Coefficient. Coefficient. So let's read Article 30. The numeral coefficient of a quantity, the numeral coefficient of a quantity is a number prefixed to it, showing how many times the quantity is taken. The numeral coefficient. So if we take a quantity A, and we say we'd like to multiply A 4 times, we would write 4A, and this is equal to 4 times A. All right? 4A. We saw that before. This number 4 is the number of times we're taking the quantity A. We're taking the quantity A 4 times. This number 4 is called the numeral coefficient. And this word coefficient is a fancy word that has a simple meaning. Coefficient just means cofactor. That's what coefficient means. 4A, when we say 4 is the numeral coefficient, we're simply saying 4 is a factor with A, and it's a numeral. It's a numeral cofactor, a numeral coefficient. So whenever you see the word coefficient, this is the key. Whenever you see the word coefficient, it just means factor. Okay? A numeral coefficient is a factor that's a number. You got that? Very simple. Keep in your mind, coefficient, it just means a factor. Numeral means it's a number, not a letter. In the next rule, Article 31, we read about a literal coefficient. A literal coefficient is a quantity by which another is multiplied. So a literal, if I had AX, A is a literal coefficient of X. It's a letter, it's literal. 4 is a numeral. So AX is equal to A times X. And A is a literal coefficient of X, just like 4 is a numeral coefficient of A. The word coefficient just means cofactor. It's a factor with the other quantity. You got that? Okay? Numeral coefficient and literal coefficient. And this gets more complicated in Article 32, because what happens if we have 5AX? We know that this is equal to 5 times A times X. 5 times A times X, but Article 32 tells us that the coefficient of a quantity may consist of a number and a literal part. Thus in 5AX, 5A may be regarded as the coefficient of X. So if there's more than one coefficient, we can say that 5A is the coefficient of X. And it's a combination of both a numeral coefficient and a literal coefficient. So numeral just means letter, numeral just means number, literal just means letter, coefficient means factor. Okay? You're going to have to study these articles yourself, but coefficient just means factor. Numeral means number, literal means letter. Anytime there's no coefficient written, anytime that a quantity is written, like the quantity A, and there's no coefficient, it does have a coefficient, it's 1. So A, the quantity A doesn't have any coefficient, but it does, because 1A is the same thing as A. Okay? Anytime a quantity has no coefficient, we can understand that 1 is its coefficient. All right? That's Article 32. Article 33, the power of a quantity. Where are we at with time?
48 minutes.
48 minutes. Let's actually stop here at Article 32, because we've got some important terms left to study, and I don't want to try to squeeze them into the last 10 minutes. So in this second lesson, we've covered Articles 16 through 32. All right? We've covered some of the basics of the signs and expressions in algebra, and we'll save Articles 33 through 38 for our next lesson. So we'll cut off there with Article 32. So in this lesson, we've reviewed the content of a high school mathematics program, and we've talked about where algebra fits into that. We talked about the definition of algebra, which is found in Article 15 in your textbook. And in this lesson, we've discussed the signs that are used in algebra, why the signs are used, what the signs mean, and we left off with Article 32, and we'll pick up in our next class with Article 33. All right, that's all for Lesson 2.